Okay, so in 2016 parametric equation, you're going to see in just a second, although this one's fairly straightforward like a lot of the other parametric equation examples that we look at, there is a bit of a trick to this one. It's not hard, but you just have to realize what you're given. So let's go ahead and jump in and look at that. So we got this problem right here. It says at time t, the position of the particle moving the xy plane is given by x of t of y of t. Where dx dt, so far so good, it gives us dx dt. Then it says the graph of y, consisting of the three line segments, is shown in the figure above. Now what we have to realize is that this is not an equation or a formula or a function of dy dt. This is the actual y position at all given times, which changes how you do the problem. Then they also give us this initial position right here as well. Now again, it's just going to change a little bit how we do some of the problems, but it actually in some ways makes it easier at least to type into your calculator once you realize what it's asking you to do. So the first thing it wants to know is find the position at time equals 3, which means I need an x value and I need a y value. Well, the y value in this case is really, really easy because that's just the y value right there, and that's negative 0.5, okay, because it is 3 line segments halfway between it's negative 0.5 or negative 1/2. To find the x value, we take our initial condition, so this is my x value right here, my initial x value plus the integral from 0 to when it wants it at 3 of our dx dt function. And when we do that, we get 14.377. So there is my position at time equals 3. Now again, a little bit tricky because we're given two different functions, two different formulas, two different types of things, but hopefully that makes sense on how to find the position. Letter B wants us to find the slope of the tangent line at time equals 3. Remember, that's dy dt divided by dx dt, and it wants us, once we find that, to plug 3 in. Well, what we have to realize, dx dt, that's pretty easy. We just go 3 squared plus the sine of 3 times 3 squared. That gives us our dx dt. That goes on the bottom. The dy dt, what we have to realize is that what it wants is the slope of that line right there. And that slope is 1/2. Okay, because it's going up 1 over 2 is we find the slope there. And when we do that, we get for the slope basically 0.050. Okay, so there's your slope of your tangent line. Now again, a little bit trickier just because we had to actually find the slope to find dy dt because that is a function of y. But now we know that the speed of the particle is actually really easy because remember the formula for the speed of the particle is dx dt, so I just go 3 squared plus sine of just what we barely did, 3 times 3 squared. And all of that is going to be squared. There's my dx dt. And now I know dy dt at time equals 3 is that same 1/2. So I'm just going to go plus 1/2 squared. Again, a little tricky at first, but as soon as you realize how to use this, it's not that bad. When you do that, you get 9.969 or 68, depending on how you typed it into your calculator or how you're rounding. Lastly, I have to find the total distance traveled from time equals 0 to time equals 2. Now this one's a little bit tricky because I'm actually going to have to do two different total distance traveled because my dy dt changes at time equals 1. So I'm going to have to do one from 0 to 1 of the square root of dx dt squared plus, now my dy dt at this point is negative 1/2. Or excuse me, negative 2, I apologize. Negative 2 because it's going down 2 over 1. So I go negative 2 squared. So that would be my first part, and then I'd have to do another one from 1 to 2 because that's a different slope. So my dy dt there is different. Everything else still stays the same. So I get dx dt squared plus, there's a slope of 0 there. So I get 0 squared. And then I go dt. When I type all of that into my calculator, what I get is 4.350 or 4.349, depending on how you type it in. So again, the tricky part about this one is realizing that we have a different dy dt depending on where we're talking about it in the problem. But hopefully that makes sense. After you figure that out, it's still the same formulas that we've always used. It was just a little bit tricky getting that dy dt. So if you have any questions about this or any other problems, please let me know.